Okay, let's continue with soil mechanics, foundation engineering plus. So we will continue with numerical methods used in modeling in geotechnical engineering. Okay, I think this is the second video on this section of this chapter. So, and it will be the last one. Okay. We will talk about formulation of finite element method. Formulation of finite element. This is just to show you what the software we are using every day, what kind of formulation these software are using, or what kind of formulas people who did the coding of this software did use. Okay, you have to know that the first step in the formulation is to determine the type of element for modeling. So for those who have used numerical modeling, they know that there are different type of elements, okay, to use. And the strain field at any point of the selected soil element is then expressed as nodal deflection. So you divide your study area, your domain, to like small pieces, and the thing you need to do is to study the deflection of each node. I'll show you some example now. So there are many type of element that are used depending on the loading situation. Okay, if you take 3D element, for example, you can have this type or this type. 3D and this is 2D element. In case of 3D element, we may have this type of element. Okay, so it's same. Sometimes you may have this or this, the same shape, but the number of nodes are different. For example, here you have 4 nodes, but here you have 10 nodes. Same here, the same shape, but the number of nodes are different. This one is 6, 15, okay, 8, 20, and so on. So you have the first step you do is to choose a type of element you want to deal with, you want to use in your numerical analysis. Okay, so in geotechnical modeling, it's better to use the type of element that can be able to adapt convenient shapes, because when you are modeling some geotechnical structure, some structure have complicated shapes, so you better use a element type that can be very convenient for any type of shape, such as like a curved shape, curved boundary. Okay, so some people are saying maybe this type of element are better, but it doesn't matter which type of element you are using. What you need to understand is what is going on the nodal point. For example, this type of, if you use this type of element, what is going on at this node, this node, this node, this node, because these nodes are what we are going to study. Okay, so we are going to talk about standard nodal shape function, the function of each node at each node. This is what we need to know. Then there are many type of function element, a standard nodal shape function for many elements. We can find them in literature. So here is, for example, just example illustration. This kind of element here, for example, or this tetrahedral one is used for this modeling, for example. Some people are saying this is the better way to capture more like strain and stress. Okay. And same here, or this case of foundation is using also same type of element modeling. But this one, for example, is using this type of element, or this type, or this type. So I think this is the type used here. This one or this one. Okay. So the first step is to choose what type of element you are using. Some software have many type. Some software have only one type of element. You don't have choice. Okay. Yeah. This one is maybe simple in terms of calculation. These are more complex, but maybe more interesting in terms of like capacity, in terms of better result. But the difference is not that much actually. Okay. So the significance of nodal shape function at each node. Okay. If we take, for example, quadrilateral element before four node element, okay, we take n, the nodal function n for each node, the number of nodes. If we take four node, this four node, 1, 2, 3, 4. Okay. This j, nj, j from 1 to 4. 1, 2, 3, 4. Okay, this rectangular. The number of nodes. This function, this n can be coordinate, it can be displacement, it can be velocity or acceleration if you want. Okay, at any point. So we can, if you want, you can decide what is the nodal function for the coordinate. What is nodal function nj for the displacement of each node. So after dividing the domain in several elements, what you need to study is the node now. Each node, the displacement of each node, the velocity of each node, deformation of each node. Okay. And after gathering everything, you will obtain the total displacement of total stress or total strain. Okay. This is what we are calling shape function. So this is, for example, how it goes. Okay. In this formula, this nj, this is coordinate system. This one, this is the shape function for the local node j in the local isoparametric coordinate. This is a parametric coordinate. So that is to say, this is just for the coordinate, the shape function for a given node, for example, 1 here or 2, it doesn't matter. Coordinate a shape function for local node in the local isoparametric coordinate. Okay. And this one, this part of this equation, this formula, is time variation of any physical quantity, coordinate, displacement, velocity, or acceleration of any given node. So I is representing the physical quantity. For example, I can take coordinate, I can be displacement, I can be velocity, or if you want acceleration. G, the J is for just the number of nodes. For example, if we can have here U in the place, at the place of I, we can choose displacement, for example. Okay, so we have U time function for displacement at node number 2, for example, because J is for the node number. Remember that. J is for the node number and I is for the physical quantity. So time variation, this is UT time variation for this. And the final one, this means UIT. It means if you take for a given, I told you I here is representing this physical quantity. If you take in case of displacement, for example, if you want, it means if you want the displacement, time function of displacement, UIT, for example, here, you have to summarize. It is sum of additioning all the 4 nodes, 1, 2, 3, 4, all the 4 nodes, for example, we see J from 1 to 4. Okay, and node 1 for node 1, node 2, node 3, node 4. The coordinate and the time function of displacement for each coordinate, multiplying, and you do by additioning everything, you will get the time function of displacement, time function of coordinate, time function of velocity. So this is what the N here is what we are calling here nodal shape function. Okay, I will just keep it here. We have an example here of this shape function. Okay, the N here, Nj, 1, J is 1, J is 2, J is 3, J is 4. Okay, this is just example using in the isoparametric parametric bilinear quadrilateral element. So in case of static behavior analysis of any structure, the time variation isn't necessary. We will not need any the time variation. Okay, and that will help us to simplify the modeling significantly. Okay, in that case, the U represents only the displacement of the point or the node of interest. Okay, only displacement. The time function is not, because it is static, and when the behavior is static, maybe it doesn't depend too much on time. So how about the strain now? The strain at any location can be expressed in terms of differential from the displacement. Okay, so you have the displacement here, for example, and from the displacement you can obtain the strain. Okay, at any point, and this is the equation the formula for the strain here. Strain, and you have this matrix B. We will talk about this matrix here later. And you have here the displacement. U here is the displacement. Okay. At any point, any node, you can obtain, after obtaining the displacement, you can then obtain the strain using this strain displacement matrix B. Okay. For in case of plane stress or plane strain situation involving two displacement, you have this U and V, for example. Displacement, this is for the displacement function. And the strain can be obtained like this. The B, the strain displacement matrix B is here, expressed in here. So the in X, Y, and here Y and X. Okay, using the partial derivation. Okay, so you can obtain the three component of the strain. Okay, so if you don't know what is the meaning of plane strain, or here is an example. We have plane stress, plane strain, in axisymmetric condition. What is plane stress? What is plane strain? What is axisymmetric? Plane stress means if on this plane, for example, the stress doesn't change on the Y, on the Z axis. Okay, the plane strain condition, it means along this length, for example, the strain is not changing. So you just need this section. The change is happening only in this section. I can take, for example, in the case of a strip footing, or let's say embankment, long embankment, for example, or a dam. Okay, if you have loading, uniform loading on a strip footing, let's say very long footing. Okay, along this footing, the load is same. Okay, no matter if you, let's suppose that this is, for example, our foundation strip footing, and the loading is on the foundation like this. No matter which section, this section, for example, if you cut, it will be same as when you cut the middle section. The stress at each section, when you cut this section, cut section here, here, it will be same. So for this kind of condition, for example, you can just take a 2D shape and study just one section, since all the sections are same. That is, for example, a plane strain situation, loading condition. Here, axisymmetric loading condition, in that case, it is like a cylinder, for example. So there is variation following the R, the radius of the cylinder, and the Z axis. And you can have like the angle. You see theta here? This theta is like the angle of when you are moving around the perimeter of this cylinder. For example, if you have the axial loading of pile, it will be exactly this kind of situation. So the example we gave here, 2D, is for this two, plane stress or plane strain. Okay, in that case, this matrix strain displacement matrix will be like this. Okay, so if you replace this here, you will have the strain as a function of displacement. Okay, so from displacement you can get the strain. Okay, the strain field at any location can be expressed in terms of differential form of displacement field at any point. So same, but right now we are going for now 3D axisymmetric. This case, for example. So I gave you example here, axial loading of pile, for example. If you are doing axial loading of pile, you will be exactly in this case, in this situation. Okay, 3D axisymmetric situation. That can be described by only two displacement. Okay, the U and W displacement. And the strain, as you can see here, the variable we have here, you have R, and you have the angular displacement. For example, if you start here and you come here, what will be the angle between this displacement? Okay, and of course you have the Z axis, and X and Y. So in that case, you will need the strain in R, Z, theta is the angle, and X and Y. So the matrix will be like this. The B matrix, the strain displacement matrix, B matrix will be given like this. Okay, so partial derivation. The strain component can be then related to the corresponding stress, because it is stress that is causing strain. Okay, stress causes displacement, and from the displacement we have our the strain. So we need a relation between stress and strain. Okay, the strain component can be related to corresponding stress. This is advanced soil mechanics. Okay, so I don't think that bachelor degree student understand this very well, because this is advanced soil mechanics. So anyway, the relation when we link stress and strain, it is constitutive relation matrix. So you can hear a constitutive model, okay, for the yielding function. So do you remember the strain we obtained? The function for the strain is here. Okay, then the relation between the stress, this is stress, this is strain. We need another matrix to link these two, and it will be the constitutive relation matrix. Okay, this is for 2D plane strain on plane stress. Again, these two situations, we have something like this. This is the stress. Okay, for 3D situation, in this case of loading, we have this as a matrix for the stress. 2D, 3D for the stress. Okay, and then in the case of soil or structure element that exhibit elastic behavior, this D matrix, do you remember the D matrix is the matrix that links the stress and strain? It can be expressed for plane strain condition as follow. This is the D matrix. This is what the software we are using every day. This equation, this formula, this is what the software are using. The code, people who are coding software are using this kind of formulation. Maybe you just need to know what is going on in the computer, even if you don't need really to understand this equation, because maybe your computer will be doing it already. Okay, so this E, of course, and this and this one and this one, these two parameters are the elastic modular and Poisson ratio. Of course, I think you know that already. Okay, the Young modulus or elastic modulus, if you want, and the Poisson ratio for the material. Okay, So similarly, for the incremental form of this equation can be used. Instead of going like we can go like small increment. If you go by small increment, you can do a nonlinear elastic behavior. If you reduce the path, the increment of everything, it is possible to do nonlinear elastic behavior. Okay. So that is in case low stress level. Okay. So this small, you see this delta, this means increment of sigma of the stress, and you have your D matrix here, the same here. In this case, the D matrix will be different. And this is small strain. Okay. It is same as this one, but this one was like a non-linear for linear elastic behavior. In case of non-linear, you just need small increment of this. Can you see the same formula is almost same as here. The difference is that here the increment, we are using small increment of the stress and the strain. And in that case, the D matrix will be different. The D will be different, okay? In the previous one, the D was not same like it. Let me go back to show you. This is the previous D for this equation. For nonlinear elastic behavior, we have this. But this is for plane strain condition or plane stress, okay? So axisymmetric condition is like more complicated. So these two parameters are then instantaneous, let's say tangential elastic modulus and the position ratio applied to the current, the considered stress level respectively. Okay. So this is what we can do, like a formulation of the numerical modeling. This is standing for, I said it before, plane strain or plane stress condition. However, the yielding of soil that govern is the one that is governing the behavior of foundation in most loading cases. Okay. Any loading cases, the yielding of the soil. Yielding of, what is the meaning of yielding of soil? When the soil behavior becomes plastic, okay, this is what we are calling yielding. Okay, this is what is governing the behavior of foundation. Because of that, some soil constitutive relation that are commonly used to model the yielding study, that means plastic behavior of soil, will be discussed in the next section. Okay, if you see the yielding, let me show you in the next section. It is here. So next time, this is what we are going to do here. You can see yielding of soil. Okay, so this is section 1.8. Section 9, we will study some yielding constitutive function for the yielding of the soil. So yielding is like to describe the plastic behavior of soil. Okay, because the yielding of soil is what is governing the failure of foundation, not only foundation actually, of any soil. So soil constitutive relation are used for that. Okay, so we will come back on this next time. So if we now combine these two equations, do you remember this equation for the relation between stress and strain? And this one is relation between strain and displacement. From displacement, you use this matrix B to get the strain. And after obtaining the strain, you use strain and with this displacement matrix to obtain stress, and inversely something like that. Stress linked with, actually we use the displacement to obtain strain, but we link then the stress and the strain together by using this matrix. Okay, does that sound better? Maybe by combining these two equations, you just replace this. You see here the strain here. This, instead of putting strain in this equation, we just replace it by this. So we will have to deal with these two matrices, D and B. See, this portion is just here. We replace this strain here by this value. Okay. Then we have the relationship directly from displacement to and displacement and stress, a relationship between these two. So at each node, remember, each node in the numerical analysis, this is what happening. So when you push, you loading foundation, and the displacement of the node, the velocity, everything, displacement of node will be linked with the stress causing this displacement. Okay. All right, we are just going to stop here and continue with this next time. Thank you very much for your time, and see you soon.